Hello again, everyone, and welcome to the next installment of the Cosmic Adventure Lecture Series. My name is Dr. Valerie Rapson, Assistant Professor in Physics and Astronomy at SUNY Oneonta and past Director of the Dudley Observatory. Today we have a really exciting topic to cover, the 2020 Nobel Prize in Physics, which is all about black holes. As you may have heard, there were 3 astronomers that were awarded the 2020 Physics Prize. And all of them had a hand in discovering black holes or proving that black holes could exist. So in today's lesson, I will introduce you to the 3 Nobel laureates. We'll talk a bit about the history of science that led up to their discoveries, and then show you the final results that are worthy of the Nobel Prize in Physics. To begin our lesson, let me introduce you to our Nobel laureates. At the top, we have Roger Penrose. He was awarded the 2020 Nobel Prize in Physics for the discovery that black hole formation is a robust prediction of the general theory of relativity. Basically, Penrose was the person that proved that black holes can exist in real life. He showed that gas clouds or stars or real life objects could condense down to form a singularity, which is essentially a black hole in outer space. At the bottom, we have Reinhard Genzel and Andrea Ghez. These are 2 people whose teams independently discovered the supermassive compact object at the center of our galaxy. Knowing that black holes could exist in real life, Genzel and Gez's team did some amazing observations of the motions of stars at the center of our galaxy and proved that at the very center there must be a supermassive black hole. So to explain to you all the amazing work that these teams did, we're going to actually go through history starting way back in the 1600s. We're going to begin by reminding ourselves of the properties of light and how gravity works, progress up through Einstein's theory of relativity, and ultimately arrive at Penrose's proof that black holes can exist. Once we know that black holes can exist, we can now take a look at Genzel and Gez's work, where they actually monitored the motion of stars and showed that at the center of many galaxies, there are indeed supermassive black holes. We begin our journey in 1676 with astronomer Ole Romer. He was actually the first person to determine the speed of light. By observing Jupiter's moon Io and watching it orbit around and predicting exactly when he would see it cross in front of or behind Jupiter, he was able to determine through delays in the eclipse timing that the speed of light must be a finite number, that light must actually take time to travel from one place to another, and it therefore has a certain value for its speed. The speed of light works out to be 3 times 10 to the 8 meters per second, and we often write it as the letter c. So as you see the letter c later on, you'll know that that just represents the speed of light. Now in the 1600s, that's all we knew, how quickly light traveled. It wasn't until 1905, when Einstein came up with his theory of special relativity, that we started to understand more about the implications of the speed of light. Things like the fact that nothing can travel faster than the speed of light, that it's a cosmic speed limit. And also that information travels at the speed of light or slower, but nothing can travel faster than light, so we can't get information faster than the speed of light can carry it. So it's just important to understand exactly what we knew when. As we start to fit the puzzle pieces together, you'll see how astronomers and scientists built upon previous work and started to apply the knowledge that other scientists had proved over time. Now that we've learned a little bit about the properties of light, we can move ahead towards the laws of gravity. It was Isaac Newton in 1687 who came up with the comprehensive theory of gravity. And his theory basically said the more mass an object has, the stronger the force of gravity it possesses, and the faster one must travel to escape that pull of gravity. We can use the Earth and Jupiter as a comparison object to explain this here. The Earth, of course, is a smaller planet with less mass, and therefore it has less of a gravitational pull. Jupiter, a larger object with more mass, has a stronger gravitational pull. Now, if I were to launch a rocket from the surface of both objects, which it's not physically possible to do that on Jupiter, but if I could, I would have to travel at a faster speed to escape the gravitational pull of Jupiter compared to that of Earth. Because there's a stronger force of gravity, I need to travel faster to get away from that gravity. Throughout this presentation, I'm going to show you a couple equations. I don't like to do that in these talks, but these mathematical expressions are really crucial. We're not going to get into them in too much detail, but they are important to see just so that you can see some relationships. The first one here is Newton's law of gravity in mathematical form, which just says the force of gravity, F, is equal to G, the gravitational constant. It's just a number, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. I take this number and I multiply by the two masses. So in the Earth's case, for example, M1 would be my mass, M2 would be the mass of the Earth. And then I divide by r squared, where r is the distance between my feet and the center of the Earth. So the force of gravity on me by the Earth is equal to my mass times the Earth's mass times the gravitational constant divided by the radius of the Earth squared. In general, what this tells me is massive and compact objects have a very large force of gravity. So if I were to take the mass and increase it a lot, give my object a lot of mass, but make it very, very small and dense. So make r really small. A big number divided by a small number is going to result in a large force of gravity. This is basically the concept of black holes, right? I mean, Newton didn't know any of this yet, but looking forward, you'll see that black holes are just really massive but very compact objects, and this is why they have such a strong force of gravity. Jumping ahead about 100 years now, we meet Jean Michel and Pierre-Simon Laplace. These two scientists independently determined the radius an object of a given mass must have such that gravity is so strong that not even light would be able to escape. So let's take a look at this expression on the right to understand what this means. The radius of an object, r, is equal to 2 times g, remember g is just a number, multiplied by the mass of the object, divided by the speed of light squared. So if I have an object of a certain mass, I can multiply by 2g, divide by the speed of light squared, and that will tell me basically what size I have to compact this object down to such that the force of gravity from Newton's equations will be so strong that not even light traveling at the speed of light could escape that object. We could think about this in terms of Earth. So if I were to take the mass of the Earth, I could plug that into the equation and figure out exactly how big or how small really I'd have to squish the Earth down to make it so that the force of gravity is so strong that light can't escape. Turns out that size is about the size of a nickel. So I take the entire mass of the Earth, squish it down to a nickel, something that'll fit in the palm of my hand, and that would make an object with gravity so strong light can't escape. We now know that this is hinting at, the sizes of black holes. But again, the astronomers and scientists at this time didn't know that. We're still in the 1700s where black holes really weren't a thing yet. But you can see how we're starting to derive and understand properties of black holes as time goes by. We just have to wait for other scientists to start to put all the pieces together. Jumping ahead again another 100 years or so, we now meet Einstein. We saw that in 1905 he published his theory of special relativity, and in 1915 he published general relativity. His theory of general relativity was basically a set of mathematical equations that explain how the geometry of space and time relate to the distribution of matter within that space. Basically, mathematical equations that describe our universe. We know we have certain amounts of mass and stars and galaxies and all this cool stuff in our universe, and Einstein's general relativity explains how that distribution of matter, how that material is going to affect space and time that it lives in. Now, we could do a whole hour-long talk or more on the theory of general relativity, but I'm just going to point out a few key concepts that are important to understanding black holes. First important thing to know, Einstein showed us that we live in a four-dimensional universe. This is one where space and time are interconnected with one another, and you cannot manipulate space without manipulating time, and vice versa. A simple analogy is imagining yourself walking across the room, right? To move in space, time must also progress forward. There is no physical way for you to go from one side of the room to the other without time progressing forward. So if you manipulate space, if you move through space, you are also moving forwards in time. Einstein also showed that it was the curvature of space-time by massive objects that create that sensation of the force of gravity. Prior to Einstein, we could describe how gravity works in a sense that we could predict the motions of stars and planets, but we didn't really understand why gravity worked the way it does. And it was Einstein that showed us that if I have a massive object sitting in this four-dimensional space-time, it will actually warp or cause a curvature of space-time, and material will fall towards that potential well, and that is basically our sensation of gravity. Here in the little cartoon, you can see that we have a massive object, maybe a star, and then some smaller objects here, maybe planets. And the more massive an object is, the more it warps or curves or bends space-time, and the stronger the gravitational pull that it creates. So basically, this is what we saw with the Newtonian equations. More mass means more gravity, and Einstein showed us that it also is more curvature in space. That's what causes that stronger force of gravity. Lastly, he also showed a property of light rays. Light rays are going to follow the curvature of space-time. So just like you and I are moving through space-time, light is doing the same thing. And if you, for example, have a bright object that's emitting near a massive object, whether it's a planet, a star, a black hole, whatever it is, the light rays that come from the bright object, they're going to travel forward in space-time. And depending on how close they are to the massive object, they are going to follow the curvature of space-time. Basically, gravity will affect light rays. So if the object is somewhat far away, you can see that the light rays moving forward, they get curved just a little bit. But if the object is closer or the light rays are beamed towards the massive object, the closer they get, the more they curve. And ultimately, if you get really close to the massive object, you can see that light rays actually curve all the way around that central source. This is going to be very important when we look at black holes and what happens when we get really close to black holes and how light can curve around these massive objects. The last thing I want to show you here is this concept of a light cone, and I'm introducing it here because you're going to see it in pictures later, so I want you to sort of understand what this is. Einstein came up with this idea of a light cone to try and visualize this four-dimensional universe. So looking at this picture on the right, imagine that you live here on this square. And while the square looks two-dimensional in the picture, it's actually our three dimensions of space. You can imagine that it has some thickness to it. You live at the very center there, but you can move physically anywhere along that square. Time is represented by the vertical axis here. You can move up and down in time. And if you have a light beam, that light beam, when it travels forward in time, is going to spread out and kind of fill what we call a light cone. So moving upward in the diagram means the light is spreading out as it travels forward in time. If you were to look in the other direction, this would technically be backwards in time. You can see it says past light cone. This is where the light beam was. This is where the light beam is going to go and how it's going to travel in time. A way of trying to visualize this in real life, imagine that you have a funnel that you can look through with your eye. Carry that funnel, walk a couple of steps, say 2 or 3 seconds of time, walk forward across the room and then stop. Put that funnel up to your eye, look in the direction that you were walking. That is where you could travel. And the more you travel forward, the more you can see. The light will spread out. You can see more of the room through the funnel. That is that future light cone that you see here. If you turn around and look backwards, you're looking through the past light cone. Hold that funnel up to your eye and look backwards at where you were. That is where you were and where you could have traveled from. The further away you can see, the more spread out. Those are places where you could have come from to reach the point that you are at now. And then again, looking forward is the place that you can walk to from that position as you move forward in time. So try and keep those ideas in your head. We're going to revisit this idea of a light cone when we get a little bit closer to talking about black holes. All right, so Einstein came up with these equations, this math, that explained how our universe worked. And other scientists then began to solve his equations for specific circumstances. So solutions to Einstein's equations, they exist for different mass distributions, as we call them. And basically what this does is it describes the curvature of space-time under these circumstances. So let me show you an actual solution that's important to the understanding of black holes, and then I'll give you a scenario in much more down-to-earth terms to hopefully make it make a little more sense. Here is the Schwarzschild metric. It was actually solved 1 year after Einstein originally published his work. And this is a solution to Einstein's equations for a spherically symmetric, non-rotating mass. So what does this mean, this crazy math? Well, imagine taking a sphere that is symmetric, so the same on all sides, and one that is not rotating, and plop it into outer space. This solution, combined with Einstein's equations, tells me how the universe is going to curve and interact with this specific type of object. So a spherically symmetric, non-rotating object in space is going to curve and manipulate space-time in a certain way, described by this fancy equation. Now, we're not going to get into the details of the equation too much, but I do want to show you what the components mean. The left-hand side, the ds squared, this is the shape of 4D spacetime. So basically, what does the universe look like around my object? What the universe looks like is going to be equivalent to how space and time act around the object. So the first component here is a time component. Basically, how does my spherically symmetric non-rotating object manipulate time? And the rest of this tells me how it manipulates space. So our three-dimensional space that we are used to. So that's it. I just take how my object interacts with space and time, and that will describe how it curves the universe. Here's your easy to understand scenario. Imagine that you live inside of a house. The house is your universe. You are a mass inside of that universe. You can move around the house, you can manipulate the furniture, you can do certain things, but only based on your ability, because you have a certain amount of strength or a certain amount of knowledge on how to do things. So the solution to Einstein's equation for you, for the universe, which is your house, is your ability to manipulate the three-dimensional space as time progresses forward. So you can move around the furniture, And your ds squared here, the shape of your four-dimensional space-time, is a property of how much time you are existing inside of your house, and essentially your ability to move and change things within inside of your house. So that's it. We're just talking about certain masses that have a specific property and how they interact with the world around them. That's what we are solving for when we solve Einstein's equations. Now, this is just one example of a solution to Einstein's equations. There are many others that exist for different scenarios, but this is the one that's going to be really crucial to understanding black holes. As astronomers and mathematicians looked at the Schwarzschild solution in a little bit more detail, they realized that there was a very special radius, actually a couple special radii, where the expression got a little bit strange. So here's the metric again, and notice on the right-hand side that there is the letter R, right? This is representing radius, or the size of an object in space. If we plug in that special radius that we met before, R equals 2gm over c squared, the radius at which light cannot escape a certain massive object, if I squish it down to that radius. If I plug this in for these R terms throughout the equation, then something very interesting happens. Terms start to go away, they equal 0, or they start to tend towards infinity. So if I plug in this R here, I should say the right-hand side of the equation, to this letter R, I end up with the same expression divided by one another, so I get 1 essentially. 1 minus 1 is 0, and this is my time component. The time component goes to 0. That's kind of odd. And if I plug in this radius to this component here, I get basically the same thing. 1 minus 1 is 0. But now I'm dividing. 1 over 0 is technically undefined. And if we take the limit, we end up tending towards infinity. So this term now, this part of the spatial component, becomes undefined, or it tends towards infinity. That's also very strange. And Schwarzschild and others at the time didn't understand the full implications of this radius. They knew that it was special. They knew that weird things happened at that radius with their solution, but they didn't really understand what it meant. They didn't understand the implication of what it meant for the idea of black holes or singularities. We now call this special radius the Schwarzschild radius, and you will see exactly how it applies to black holes in just a few moments. To understand the importance of the Schwarzschild radius, we have to move forward to 1939, and we have to meet Robert Oppenheimer. Yes, that Robert Oppenheimer, the father of the atomic bomb. Before he worked on the Manhattan Project, he was actually doing some astrophysics. And he and his student, Hartland Snyder, they were studying just the generic concept of the collapse of spherical clouds, and that could be applied to spherical clouds in outer space. And they came to this realization that the Schwarzschild radius, which they called the event horizon, is actually a point in the previous equation where only gravity persists. And what it ultimately meant is that no information can be communicated with the outside world by anything that is beyond that radius. This is ultimately because no light can escape, right? We saw this previously, but the scientists who came up with all the previous stuff we talked about didn't quite put the pieces together. They knew that they had derived this radius at which light could not escape the gravitational pull, but they didn't quite understand that information traveled at the speed of light. It was Oppenheimer and Snyder that started to put it all together and said if information travels at the speed of light, per Einstein, then if I shrink this down so that light can't escape, if I shrink an object down so that gravity is so strong light can't escape, then no information can be communicated. I basically reach this radius, an event horizon, where no information can be gathered beyond that point. So one of the original diagrams that Oppenheimer sketched up is shown on the right-hand side and is a little bit weird to interpret the first time, but let me try and explain it to you here. This is his diagram of a collapsing star. So in this diagram, the gray blob is the star, and the left over to the right, that is the full diameter of the star. Time progresses upwards in this diagram, just like it did in the light cone picture we saw before. So as time moves forward, you can see the width, the size of the star, gets smaller and smaller and smaller. So basically the star edges come to a point because the star is shrinking. That's what the gray blob is showing. As time progresses forward, the star shrinks down smaller and smaller and smaller. When it's a certain size, it will have certain properties, but as the star approaches that special radius, the event horizon, the star will have a certain size past which any information about what happens to the star cannot be gathered, not physically in real life at least. And you can continue the collapse down. If the star literally collapsed down to a radius of 0, that would be what we call a singularity. And that is also a weird point in the Schwarzschild equations, where if you just set r equal to 0, then all sorts of weird things happen. So what did we learn from Oppenheimer and Snyder's work? Well, they showed that at r equals 0, we can generate a singularity. And they were the first to show that physical objects, such as a spherically symmetric cloud or a star, can collapse down to form a singularity, or what we now call a black hole. The math shows that the creation of singularities is possible. What was still confusing at the time is that the math only works if you assume the ideal case. You have to be a spherically symmetric object. You have to be a perfect sphere for the math to work out, to actually create the singularity. But of course, in real life, nothing is spherically symmetric. I mean, sure, planets are spheres, stars are spheres, but they're not 100% symmetric. They're not perfect. There are slight irregularities that technically would not allow a singularity to form in real life, at least not according to the work of these scientists. So Einstein was still around and he read this work and he was like, this is cool, but I don't believe that you can actually form a singularity or a black hole under real life circumstances. Now we have to see if that is actually true. Can a black hole form in real life? And that is where we are ultimately going to meet Penrose. So before we meet Penrose, we have to look at the first hints that suggested that black holes actually existed. What sparked Penrose to prove that black holes could actually exist? Well, it was these pretty objects that we now call quasars. It was in 1963 that the first quasar or quasi-stellar object was discovered. This is QSO 3C273, pictured on the right-hand side. And when you look at the picture, it just looks like a star, right? It looks like a really bright star. And if you look close, you can actually see some galaxies in the background. What astronomers realized by doing some measurements on this apparent star is that it's really far away and clearly it's ridiculously bright. Using spectroscopy, astronomers were able to determine that that object was 2.5 billion light years away. Okay, much, much further away than many of our closest galaxies, far beyond the edges of the Milky Way. So it was very, very far away, but it appeared to be 1,000 times more luminous than all the light in the Milky Way galaxy. Not just 1,000 times more luminous than the sun, 1,000 times more luminous than every star in our entire galaxy, all of their light put together. Clearly, these are weird objects. They look like stars, but they're very far away and they are ridiculously bright. So doing the quick math, you could figure it out and say, okay, well, let's pretend that this really is a star. Let's assume that it really is a star. How big would it have to be? How big of a star do I need for it to be this bright if my distance is accurate? Turns out that the star would have to be millions of solar masses. So millions of times the mass of the sun would have to be compacted together to generate this really bright star. This is not physically possible for many reasons that we don't have time to get into. The star would rotate so quickly that it would be blown apart. The pressures generated by fusion on the inside would blow the star apart to get it to be this bright. It's just not physically possible for a star to be this bright. So it must be a much more compact object that is somehow still very, very bright. And these were our very first hints that this object might be a black hole. Now we finally get to meet Roger Penrose. In the 1960s, Penrose set out to prove that singularities, or essentially black holes, could exist under real-life circumstances. Basically, could non-spherically symmetric objects collapse down and create a singularity? To figure this out, he had to introduce a new mathematical concept called a trapped surface. And this is kind of a weird mathematical thing, so bear with me as I explain it to you with some pictures. First thing to know about a trapped surface is that all orthogonal light rays converge as time progresses forward. What this basically means is if you are within a trapped surface, light will not travel outwards and spread out. It will start to curve in space-time and wrap around, ultimately converging with other light rays in the system. Here you see a NASA visualization of a black hole, and this is basically what happens in a trapped surface. Instead of light emanating outwards from the black hole, you can see that the light beams wrap around the black hole in many directions here, and all of the light rays will eventually converge. The actual black hole is at the center, so this is all material orbiting around the outside of a black hole, and we are able to see the light emanating from that part of the object. So light rays are warped around a trapped surface in curved space-time. And also within a trapped surface, time and space switch places. And this is where it gets really weird. So here's a super simple looking cartoon that takes a lot more brain power than you would expect it to. If you were to go past the event horizon, past the Schwarzschild radius, essentially inside of a black hole, space and time switch places. Outside of the black hole, you can move in a certain direction of space. Here we're moving upwards. So imagine walking forward in space. After that, once you enter the black hole, time is what moves forward. So no longer, if I move in the same direction, am I moving physically forward in space? I am just moving forward in time. That means that any material that goes past the event horizon is always going to progress forward towards the singularity. You no longer are moving around in space like you think. You are always progressing towards the singularity, which is forward in time. I know, kind of weird, but hopefully it'll make a little more sense as we keep going. Using this concept of trapped surfaces, Penrose ultimately mathematically proved that a spherical surface that has a radius smaller than the Schwarzschild radius is a trapped surface. So he took this theory of trapped surfaces and he proved that they were actually a real thing, that inside of the Schwarzschild radius, you are trapped, essentially. This led to the idea, the concept, that a black hole is technically a trapped surface, right? Black holes have an event horizon, and inside of them, you are within that trapped surface. What does it mean to be inside of the trapped surface? So let's take a look at the cartoon on the right. This is kind of similar to the picture I showed you from Oppenheimer, where you have an object, material here, the pink blob, that has a certain diameter or radius, and it is collapsing down as time goes by. So time is progressing forward, the material is collapsing down to ultimately form a singularity. Eventually, the material will collapse down to a certain radius, a certain size. This is your event horizon here. And if you are inside of that event horizon, if you're inside that trapped surface, then you can never escape. If you are outside, things are a little bit more normal. Now, if you notice here, there are some of those light cones that we saw before. Each one of the dots represents an observable object that is falling towards the singularity. And the yellow is basically time progressing forward. And the dashed lines is time progressing backwards, right? Because remember, light cones are showing the location of where light would be forwards in time and backwards in time. Outside of the singularity or outside of the event horizon, you've got a normal light cone at different points in time. Inside the singularity, the light cones always, inside the event horizon, the light cones always point towards the singularity. Time, as we said in the previous slide, always progresses forwards towards the singularity. So to escape a black hole, to escape an event horizon or trapped surface, you would have to travel not only faster than the speed of light to escape the pull of gravity, but you would also have to travel backwards in time. Since you are always moving towards the singularity, you'd have to go faster than the speed of light, which would mean moving backwards in time to escape. So that's not physically possible, right? At least not in the universe that we know. So once you are past the event horizon, nothing can ever escape. And that is more like our modern understanding of a black hole, right? Once you fall in, you can never ever get out. So Penrose went on to do a ton of mathematical work to prove that the previous concepts we discussed are actually practical in real life. He showed that trapped surfaces occur when you have a non-symmetric object collapsing and even a non-symmetric rotating object collapsing. You can create a black hole under real life circumstances. That was the ultimate goal, and that is what he ultimately proved in 1965. With this knowledge, astronomers and scientists went on to apply that knowledge to quasars and other interesting objects in the sky. And they were able to show that 3C273, our quasar from before, was indeed a supermassive black hole where the light that we were seeing was generated by material falling towards the event horizon. This ultimately led astronomers to speculate that most galaxies in our universe likely have a black hole at their center. And this is now where we move into our next Nobel laureate's work that ended up with the discovery of the supermassive black hole at the center of the Milky Way. Now that we know that black holes can exist in real life, astronomers can look towards the centers of other galaxies and try and actually discover their presence. It's only been recently, within the last couple of years, that we have the ability to photograph black holes, and really we only have one example of it at the moment. The picture on the right is an image of galaxy M87, that's the blue and yellow blob in the background. And if we zoom in towards the center, at radio wavelengths, we see two jets that are supposedly coming from a black hole. And if we zoom in towards the center and use a bunch of ground-based telescopes, combine the data together, we can actually take a picture of the light orbiting around that black hole at the center. This is our first, and at the current time, only direct image of a black hole at the center of a galaxy, or really the direct image of any kind of black hole. Historically, to find black holes, what we have done is not taken direct photographs, but actually used kinematics. So the best way to show a black hole exists is not to directly see it, but to infer its existence by watching gas or stars orbit around it. What we do is we use something called Kepler's third law to determine the size and the mass of an object. Kepler's third law is shown down here. We normally apply this to stars orbiting one another or planets orbiting the sun, but it really applies to any two orbiting objects. It says that the period squared, so the time it takes an object to make one complete orbit, is equal to the distance between the center of the object that is creating the gravity. So in a circular orbit, that would be the center of the circle cubed, multiplied by this set of information, 4 pi squared divided by g. Those are all just numbers. And on the bottom here, we have the sum of the masses. Capital M is the mass of object. So in the case of the planets and the sun, capital M would be the mass of the sun. And then to that, we add the small and usually insignificant secondary mass. So what we can do here is use Kepler's third law, and we can watch a planet, let's say, orbit a star. If we determine the period, time it takes the planet to go around the star, and the distance that the planet is from the star on average, we can calculate the mass combined of the star and the planet. And usually the mass of the planet is so insignificant that we're basically just determining the mass of the star. We can apply this exact equation to stars or gas at the center of galaxies to determine the mass of black holes. If I watch a star or a clump of gas orbit with a certain period and a certain distance from the center of the galaxy, I can calculate the mass. And then we can use some visual images and the distance between the star and the center to get a rough idea of the size of the object as well. This will help us determine whether or not the stars or the gas are orbiting a star cluster, a black hole, or some other object at the center of galaxies. Using this technique of measuring the motion of material around the center of a galaxy, astronomers were able to make the first discovery of a black hole at the center of a non-quasar-like galaxy. Here is a picture of that galaxy. It's NGC 4258, also called M106. You can see that it's a lovely spiral-armed galaxy, probably similar to our Milky Way, with a very bright center. And by watching how material orbits the very center of the galaxy, astronomers figured out that there's 37 million solar masses of material packed into a space less than half a light year wide. That's an incredible amount of material in a very small amount of space. That density is much too high to be a single star or even a star cluster that we're not able to directly observe. It has to be a black hole. There's no other physical object that we can think of that would have these properties. So this really got astronomers thinking about the possibility of black holes at the center of all galaxies, especially black holes at the center of our own galaxy. To figure out if our own Milky Way has a supermassive black hole at the center, we have to look towards an object we call Sagittarius A star, often written just SGR-A asterisk. This object is a bright radio source that astronomers discovered at the center of the galaxy. And let me try and put things into perspective for you. Here we have a cartoon of the Milky Way galaxy. The bright center here would be where the supermassive black hole is. And we live out here on the Orion Spur, a spiral arm about 26,000 light years away from the center. If we zoom into the center and actually observe this, we can get real photographs of the center. And this is a radio image of Sagittarius A and the very bright spot at the center, Sagittarius A star. So this is just a blob of gas and stars that is at the very center of our galaxy. And if we zoom in specifically towards this central cloud and try and get a good look at Sag A star, we can switch now to an infrared and an X-ray view. Here is that same region. This view allows us to see many more stars. And zooming into the brightest spot, we can see that there's a bright X-ray source right at the location of Sagittarius A star. This is suggesting that there is a lot of hot material, stars, that are falling in towards a supermassive black hole at the center of the galaxy. But to actually determine if there's a black hole there for sure, we need to use kinematics. We need to watch some material orbit, we need to watch some stars orbit, and actually get a size and a mass for that central object in the middle of our galaxy. So that's exactly what our second set of Nobel laureates did. Reinhard Genzel, he observed the galactic center using some telescopes at the European Southern Observatory. For example, he used the set of telescopes called the VLT, the Very Large Telescope. Each one of these domes has an 8.2 meter diameter telescope inside. And Andrea Ghez observed with the Keck Observatory in Hawaii, a pair of 10-meter telescopes. Both astronomers observed at infrared wavelengths, and this was going to allow them to see through a lot of material that exists between us and the center of the galaxy. That's one major challenge that we have in all of this, is that there's a lot of stuff between us and the center of the galaxy. So we can't just point a regular telescope and see the black hole. We have to use wavelengths that can easily penetrate through the material between us and the center to allow us to attempt to actually see the objects at the very center of the galaxy. So they use the infrared capabilities of the ground-based telescopes to do just that. Along with having to use infrared wavelengths to peer through gas and dust to see the galactic center, the astronomers had one other big challenge to overcome: Earth's atmosphere. Since they were using ground-based telescopes, they had to look through the atmosphere of Earth. And of course, you know, we have wind and weather and turbulence that naturally exists in the atmosphere around our planet. When you observe with ground-based telescopes, the atmosphere often blurs your images, and you don't get as high quality of an image as you normally would. Here's a couple of examples just to show you what the effects are like. Here is an image of Jupiter. On the left, when we have what's called good seeing, or really good conditions, calm air, not a lot of turbulence, no clouds, we can get a great picture of Jupiter. Bad seeing, when the atmosphere is very turbulent, we get a blurry image on the right. Clearly not as useful as the one on the left. Here's a quick comparison of an image of a galaxy from a ground-based telescope and one with the Hubble Space Telescope. You can see just how much the atmosphere affects this image. The galaxy looks like a blurry blob, whereas the Hubble image above the atmosphere shows a much more crisp, clean image of this galaxy. So Ghez and Genzel, they needed to have really nice high-resolution images to be able to track stellar motions. Seeing a bunch of bright blobs blended together was not going to be helpful. They needed to view individual stars and track their individual motions to infer the presence of a black hole. So they had to overcome this issue somehow. Initially, what they did is they just took really short exposures. And by taking really short exposures, you were basically counteracting the changes in the atmosphere. The shorter your picture is, the less time you allow the atmosphere to blur your image. They can then stack the pictures together and create a longer exposure, the equivalent of a longer exposure image that is much more clear than if you actually took a multi-minute picture of the night sky. So in the late 1990s, they got their first set of results. The image on the right is from a paper by Eckert and Genzel in 1997. And what you are looking at, the black blobs are individual stars near the galactic center. And the center of the galaxy, Sagittarius A star, is represented by the little orange star right there. The astronomers were able to distinguish some individual stars, and they were able to track how quickly they were orbiting the galactic center. Any black circle that you see an arrow pointing away from, that is a star where they were able to track the stellar motions. The key thing to notice here is that stars that are closer to Sagittarius A star are moving faster. Their arrows, representing speed or velocity, are longer, so they're moving faster. And the stars that are farther away from the center are moving generally slower. That is a property of Kepler's laws. We would expect the stars that are closer to the center to move faster and stars that are farther away to move slower. And by tracking these stellar motions, we saw that the stars were following Kepler's laws, so we could indeed use them to potentially measure the mass of the center of the galaxy. And based on these stellar motions, they started to think that, it appeared that there was a black hole at the center. They didn't necessarily have the precise measurements yet, but all these stars appeared to be orbiting around essentially nothing. There wasn't a really bright, massive object at the center that they looked like they were orbiting around. They appeared to be orbiting around a singularity based on the kinematics that were observed. But ultimately, to really figure this out, we needed precise measurements, just how massive and just how compact is the central object. And to figure this out, the astronomers needed even better data. So to get better data, we had to wait for new technology to be developed. And this new technology is called adaptive optics. Adaptive optics are an amazing engineering feat. And basically what the idea is you have a telescope mirror that is deformable. It can actually change shape to counteract the atmospheric effects. So here's a little cartoon that shows simply what happens. Light comes in from outer space through the telescope, and it strikes what we call an adaptive mirror. This mirror is deformable. It can change shape to counteract the atmosphere. That mirror counteracts the effects of the atmosphere. The light bounces off that mirror. Some of the light, which is now corrected, hits our detector and we can take a picture. Basically, the light beams have corrected for the distortions in the atmosphere. The image will no longer look blurry. A small amount of light is sent back through the system. So it goes through a wavefront sensor and a control system. And this little bit of light is what the computer uses to change this mirror. The atmospheric effects change thousands of times a second. So we have to make very quick and precise changes to the mirror to accurately adapt for changes in the atmosphere. And that's literally what this mirror does. It changes shape ever so slightly, hundreds to thousands of times a second, actively correcting for those atmospheric effects. It is really just amazing. Here to show you what you can get, on the right-hand side, we have an image of Saturn. Here's a picture of Saturn without these adaptive optics in use, and here it is with adaptive optics in use. Same exact telescope, same exact equipment, just one with and one without adaptive optics, and you can see the difference. With adaptive optics, astronomers can get images that are just as good, if not better, than space telescope images. So it's just truly amazing. This is the technology that is necessary to get the images that we need of the center of the galaxy to track those stellar motions. So with adaptive optics on the Keck Observatory, Andrea Ghez was able to get really clear images of stars and literally watch them orbit over many years to get a good sense of their kinematics. The video you see on the right-hand side shows the center of our galaxy as a little white star, that's Sagittarius A star, and each one of the colored blobs is an individual star orbiting around the center. You can see exactly what the diagram showed before. As stars get close to the center, they move faster. Some of them whip around and come to the other side. And by watching these stars move around and applying Kepler's laws, we can determine exactly how massive and how compact the center of our galaxy is. This data told us that there is a supermassive black hole of about 4 million solar masses compacted into a size that is only 1 astronomical unit wide. So 1 AU is the distance between the Earth and the Sun. So imagine taking the amount of mass equal to 4 million suns and squishing it all in between the Earth and the Sun. Basically, take the Earth's orbit around the Sun, pack in 4 million suns into that space. That is what the supermassive black hole is like. So with that information, it's just not possible for this object to be anything else, right? It can't be a star cluster that we just can't see. It can't be a single luminous object that for some reason we can't see. The physics doesn't agree with anything but a black hole, anything but a singularity. So we now have no doubt that the object at the center of our galaxy is indeed a black hole. And that is what Genzel and Gez were awarded the prize for showing. Both teams' work proved that the central object in the Milky Way must be a supermassive black hole. So that's what our Nobel laureates from 2020 have been up to. We saw that Penrose proved that black holes can exist in real life, and Gez and Genzel showed that there's a supermassive black hole at the center of the galaxy. Now, these people are scholars, and they've been doing a ton of work since these original big discoveries. And we could do a whole nother hour-long lesson on what they've been doing recently. But just to briefly summarize, Gez and Genzel, for example, have been using some of the data they collected to test more of Einstein's theory of general relativity around black holes, specifically those at the center of galaxies. They also discovered some infrared flares emanating from material that is very, very close to Sagittarius A star. So that'll teach us a little bit more about the properties of the black hole at the center of our galaxy. And Penrose has been doing a lot of great work too. He created something called Penrose diagrams, which are a mathematical way to visualize curved space-time. And he's also been doing a lot of work with Stephen Hawking, proving that the Big Bang model shows that the beginning of time and the beginning of the universe started at a singularity. And he also showed how black holes can lose energy and ultimately evaporate, which is a really weird concept. So all of these astronomers and scientists are doing fantastic work, and I can't wait to see what more they're going to produce throughout the rest of their careers.